Hi, my name's Anthony, and today I'll be talking about Automatic Github Issue Labeling. So in this video, I'll just give a quick overview of what it is that we've done, and then I'll show some code, and then at the end I'll give a demo and show how someone could use and interact with the tool. So let's begin. So here's what a really pretty open source repository looks like. As you can see, every issue is labeled in some way. So this is really easy. If you're a developer and you want to work on the demo, you could just click on kind demo and see what issues are associated with the demo. So if the demo is important, then your issues are organized and you could fix your issues with the demo. But what happens usually in open source repositories is this, where since it's just regular people contributing, they really will just not tag the issues, either because they don't really know which proper tags to use or just because they don't feel like it. And the goal is to make an issue labeler that will tag issues for these people. And there's been a lot of work in this direction. So this paper I show on the right was like a 40-page survey of the field. And it tried out all sort of the basic models, for NLP problems like TF-IDF, and then it used SVMs. And it found that SVMs work really well as this word vector model called fastText. And the SVMs and fastText make up the basis of our approach, and we'll get into those later. But there was a major issue in the previous work in that it only classified bug, feature, and question, when in actuality for any given repo there's actually going to be a long list of labels. And the reason they only did bug, feature, and question was because their approach was different than sort of what we want our approach to be. They wanted to make a very generalizable model that could work for any issue on GitHub. So in every repository there's going to be bug, feature, questions as labels in the issue board. But what we want to do is we want to make it possible, for example, for there to be this component/install tag to be predicted. So we couldn't train it on all of the GitHub issue data like they did. We would have to train it specifically on the OpenShift origin repository to be able to predict this tag. So the trade-off is that their method could be generalized and more accurate because they train on so much more data, but we have a lot less data, but our models will be personalized to repositories and they'll be able to predict a lot more labels. And sort of our solution to the problem is creating a new model for every label. So for a label such as component/install, we would create a model for that says yes or no. And basically once you have 10 models for 10 possible labels, you just pass an issue through each model and you'll get a list of yeses and a list of nos, and you just output the models that give you a yes. So this method kind of gets around the issues of having imbalance with the classes, and also it makes it possible to make multiple tags for one issue. So we're going to talk about the models we use. We use two models, and I'll explain more about that in the next slide, but the two models are fastText and support vector machines. So first I'll talk about fastText for a bit. fastText is a word vector model, which means every word is transformed into a vector. And usually what should happen is that your words that are very similar to each other should have vectors that are very close to each other. So it's kind of how you find synonyms. And there's even examples of word vector models that pick up other types of nuance in the English language. And there are powerful models. Something cool is that you could pre-train this model. So you could pre-train a word vector model on a Wikipedia dataset, for example, and it will learn a lot of the English language that way. And then when you want to apply it to a specific task, it already knows so much of the English language that the specific task is easier to do. And that's what we do here. the drawback of fastText is that it needs a lot of data because it is, a very powerful model. And in our approach of making personalized tagging models for like specific repos, we don't always have a lot of data for each label. So it's possible that a single label will only have like 100 data points, which is just not going to be enough for fastText to learn things, because it is a very large and powerful model so it trains slowly. But we also have SVMs, which are just a very classic sort of classifier in data science. They've never given me any issue. And it works well on a small amount of data points, so you can only have like 30, and an SVM will still be able to pick up on something. And sort of one of the main differences here is that fastText can kind of understand English, while SVM really can't, but it can pick up on sort of obvious clues at what a tag should be. And yeah, here's sort of our approach. So I mentioned that we have a different model for each potential label. And so what we do is we take the issue data and we run it through both fastText and SVM. We train two models, and whichever model performs better, we save it. So that's sort of what our approach looks like, because you don't know if fastText is going to work well or not, especially when you have a small amount of data, and SVM will very often outperform fastText. Yeah. And so I'll go through some of the code. So another important thing I should mention is that fastText and the SVM, they have different pre-processing functions, or at least like in my example they do, and there's good reason for that. But yeah, just go through the code. So the first thing we have is issue extraction notebook. This notebook just uses the GitHub API, and here you can sort of see an example of the output as it saves every issue. There's a title, a body, a creator, and a list of labels that are separated by tabs. And yeah, that just issue extraction. And now this is the first pre-processing notebook. This is pre-processing for SVMs. And what this does is it tokenizes the data set into a set of words. First we apply a bunch of regular expressions to pre-process it. Sort of one of the main ones is that we just like delete all the code and replace it with a word called code block. This is because the code is just like very noisy, and it will make our vocabulary too big, and our model wouldn't learn anything by actually reading it. So yeah, we take all the vocabulary and then we count up the words. In this example, there was 34,000 words, but we just keep the words that make up the top 80% of the data. So it goes down to only 1,000 unique words. And this is good because when you have a very small amount of data, you just want to keep things very simple. Especially for like an SVM. Simple is going to be better if you have small amounts of data. And we'll go through now the second pre-processing step, and this is the fastText model. So we pre-train a word vector model, which is very important. So the first thing we do is we first import a word vector model that already exists. And this is one sort of put out by the fastText team. It was trained in Wikipedia and the news. The issue with this model is that it is very large. So it is 300 dimensions and has 1 million words. And since, again, we're going to have a pretty small amount of data, we want to cut it down as much as we can. And that's exactly what we do. So we delete a bunch of the words that are not useful to us, and we cut it down from 1 million to about 25,000. And then after that, we go through GitHub issue data and just count up the number of words and get the words that make up the top 95%. And so we add back in like about 140,000 words that we get just from browsing GitHub data. And after this, we actually reduce the the dimensionality. So at first it was in 300 dimensions. We do PCA to reduce it to 175 dimensions. And that basically builds just the vocabulary. And it's already, most of the vocabulary is pre-trained on Wikipedia and the news. And then we have this other notebook that fully pre-trains it. So we use a service called GitHub Archive to extract all GitHub issue data. So it has pretty much every issue from every public repository. And so we could basically set a model to unsupervised train, like pre-train a word vector model for all of the data, and that's exactly what we do. So this could train for a very long time. This could theoretically train on every single GitHub issue that's been made publicly, and yeah, it could just run forever if you wanted to. And yeah, that's just the pre-processing and sort of vocabulary building for the two models. Now we'll get into the notebook where we actually train these models. So yeah, we load in the data set. This is just like a count of the issues. You could define synonyms, you can make a list of bots who you don't want to predict. There's some customizable settings here. But at the end, I set like a cutoff of 50, and these are all the labels that are possible to predict. And now what happens is, you could train the model. So this uses, since there's a low amount of data, we use k-fold cross-validation. And here are sort of the results of the accuracy, recall, and precision. And it also says which model performed better. Little disclaimer is that none of these are actually using the pre-trained fastText model that I just described. And so most of the time SVM, pretty much all the time, SVM outperforms the fastText model. But yeah, you could actually see some pretty good results. So for something like logging, there's only 150 data points. So this means there's 75 issues that are tagged logging, and then we also randomly sample 75 that are not logging. But you can see an accuracy of 83%. And yeah, we sort of could set a criteria for which ones we want to save. So a minimum accuracy and a minimum precision. And yeah, this is what we get here. So yeah, something like metrics performed well. And yeah, we just save that when we upload it to Seth, and it's ready in our app. So now I could show the app. So yeah, here I just load in the data, and I'll also randomly sample a data point. So this is actually an issue here: deployments, POC, next steps. This doesn't even look like even a real issue, but I'll make a new one. Yeah, S2I builder failed to push, created it. Yeah. So component image registry is the only tag, but yeah, what you need is you need to make a JSON that contains the title, just as it comes from the GitHub API. The body also just as it comes from the GitHub API. It shouldn't be cleaned. And then also a created by. So the created by is important just because if it's created by a bot, the app could filter it out. And then we can send this request to this link here. And we'll, wait a second. And yep, got a 200 response, and here are our predictions. So to get component build, component image registry, component image, and kind of bug. So honestly, all of those are at least somewhat accurate. One of the drawbacks of trying to guess for every label is that you're gonna end up actually always with more labels than you're gonna want. But that is sort of the best solution we have for now. And yeah, that kind of sums everything up. So thank you for watching.